theory and study of groups. Okay, that begs the question, what is a group? So in a group, you have an idea of elements. For example, I can have A and B, and you have an idea of composing them together, combining them. You can think of this as multiplying, adding, or just if you have functions, you can compose them. And what we have is we have A and B, and we combine them together to get another element C. And this we call the group operation. And this gives the group its structure. And that's mainly what I'm going to be talking about in the rest of this talk. So what I'm going to do first is describe the definitions. So what properties of this operation do we need? What rules does it have to follow for it to actually be a group? Then I'm going to talk about how we can kind of generalize an idea of numbers. And not like numbers, but things and counting systems. Next I'm going to talk about structures. I'm going to give an example of a triangle I have hidden over there. And I'm going to talk about group action. And there's a lot more to group action that I'm not going to talk about because it gets a lot more algebraic. Michael is disappointed at me calling it group action. But it's this idea that you can have groups and they have symmetries and structures to them and they can act on things. For example, triangles or water bodies. Many things. In the third section, I'm going to talk about morphisms. Morphisms generally give this idea of similarity, a way to have one structure be similar or related to another structure. And there's different kind of restrictions on this, right? You can be more specific of how similar something is to something else. So you can say it preserves a structure, or you can say it preserves all structure, or you can say it is the same thing and it has the same structure when you look at it in a different way. And those are the three different morphisms I'm going to talk about in more depth. The fourth section is going to be a long one. This is a bit more mathematical and a bit more formal, which maybe Michael's excited about. In this section, I'm going to be covering what a subgroup is, and it's this idea of containment. You have a group, and inside you have another group. And that's very useful. It allows us to talk about kind of dividing up your structure, splitting it into pieces. And for that, I have to talk about cosets. This idea that you can have your whole group, and inside you have a smaller one. But there's a way to take this and kind of get another one that's adjacent. If you know linear algebra, you can think of this as you have a plane, and you have another plane that's parallel, and another one, and another one. And the set of all of these planes are your cosets. Then I'm going to talk about Lagrange's theorem. I think it's a very cool theorem. It talks about kind of restrictions on the size of subgroups. So if you have your whole structure, you have a smaller structure inside, how does this structure divide up your space? And actually from that you can say how many things it has to have in it. An example is if I have a group with 7 things in it, I can tell you that there are no subgroups with 3 things in it. It's impossible. I can actually even further say that there's only going to be 2 subgroups. There's going to be a subgroup with 1 thing in it, and a subgroup with everything in it. So then I'm going to get on to section 5. Section 5 is quotient groups. It's the idea that you can take a whole group, and you can actually divide it by what's contained in it. It has some restrictions on it. You can't do this with any subgroup, and I'll talk about that too. But if you actually do this, you can think of it as removing a structure. Like if I take 12 and I divide it by 4, I'm removing the factor 4. So you can think you have your group, you have a structure inside of it, and you're removing the structure. And it turns out with quotient groups, they have the really nice property that what you're left with is also a group. And there's some very useful theorems that allow you to work with these more easily that I won't be getting to in this talk. There should be resources online. Michael is again disappointed. I'm going to give an example of this with my triangle friend. And I'm going to show you how we can describe the structure of a triangle, or the symmetries of a triangle, so just the group acting on the triangle. And then I'm going to leave time for some questions and answers. So hopefully that's all good. I'm going to get started with my talk. So first, definitions. As I said, we have this idea of composition of elements. And I can kind of think of this as a box. You have a box of things, and you can take 2 things and combine them to get another thing. And this operation has 4 rules. These are in no particular order, they're just in that order. The first rule of this operation is you have to have neutrality, which means there has to be a thing, or you can think of it as an action that does nothing. If I multiply by 1, it doesn't change a number. If I add 0, it doesn't change a number. If I raise something to the power of 1, it doesn't change a number. This is the idea of neutrality. And I'm going to call this E. You can see it up here. So I have EA, it's the same as AE, it's the same as A. Throughout this talk, I'm going to be calling it 1, just because multiplying by 1 does nothing. And this kind of looks like multiplication. So that's the first property. The second property is inverse. It's this idea that if I have some action, I can undo it. Nothing is permanent. Another way to think of it is if you have an A, for example 2, then there's an inverse, negative 2. If you add 2 and negative 2, you get your identity, you get 0. You can also think of dividing. If you have 2, and you divide it by 2, you have, 2, and you multiply it by a half, you get 1, which is the do nothing. So that's the second property. The third property is associativity, and this one's a bit weird to conceptually understand, but I have some diagrams here. And the idea of associativity is that order of operation doesn't matter, right? I can take A and combine it with B, and then combine it with C, and I get ABC. Or I can combine B with C, and then combine it with A, and I get ABC. It gives me the same thing. What's important here is the order of the elements still matters. If I have A and then B, it's different, or it could be different than B and then A. That property that's the same is called commutativity, but we don't assume that for groups. It actually turns out when we do assume this, it makes groups a lot nicer. And there's a whole bunch of things that Michael's getting excited about, but I will not be talking about it in this talk. Question, yes?
Under identity, does E have to be a part of the group as well?
Yes, it has to be contained inside that. So we have to have an identity element. It works out we always have to have this. So even when I talk about groups contained in groups, they also have to have it in them. And the last property is closure. Yes?
And these definitions here are only for like our example group G? They're not for like literally every group, or?
They're every group.
Every group.
Every group, your operation has to follow these properties. So yeah, we have closure. This is the idea that when we combine these two things, we still get something in our group. If I add two numbers, I'm still gonna get a number. I'm not gonna get a letter. I'm not gonna get a cube or a water bottle, right? That would be a bit silly. And this is kind of allows us to put things inside of it. Because if everything's kind of leaking out, then it's hard to put boundaries on stuff. So those are 4 properties of groups. Hopefully that was understood. I'm now going to talk about Cayley tables. You've actually seen these before. These are not something new. These are effectively a generalization of addition tables and multiplication tables. Because as I said, our operation could be addition, it could be multiplication. Those form groups. But we're generalizing, we're allowing more possibilities. This kind of table describes how to combine two things. So for example, if I wanted to do A times B, then I find the 8th row in the B column, and I get C. So AB equals C. It works out this one actually has the switching commutative property. AB equals C, but BA is also C. You can see that in the symmetry of this table. If I flip the two things, it stays the same. This is very useful because it allows us to see what the structure is. We can see immediately there are these ones along that diagonal. They kind of stand out. And this means if we combine A with A, we get 1. B with B is 1, C with C is 1. And you can kind of think of this as a flipping action. If I take a thing and I flip it, and then I flip it again, I get back to where I started. That's what it's saying. When you do A and then A again, you get back to where you started. It does nothing. And there's a fancy name for this. This is called the Klein-4 group. It's not really that special. It is one of the first kind of infinite groups, but I won't actually be talking about this. Yes.
All elements of the Klein-4 group are self-inverse, right?
Yep.
Okay.
Yes, and you can see that because of this diagonal. Right? So every element is its own inverse. And you can actually check that we have the 4 properties that I listed above. You can also talk about this group as the symmetries of a rectangle or rectangular prism under rotation, which is interesting. So I'm going to be giving an example of the triangle. The triangle is a lot simpler. So, on to section 2. I'm going to be talking about structure. And for this, I'm going to bring up my triangle friend, right here. And so, this is the idea that we have some group, and it's acting on a thing. And what it does is this group actually describes their symmetries. So we said that this is the triangle, this is also a triangle, this is also a triangle. We can rotate it and it doesn't change. I have indicated a face so that you can still see the direction, but I think it's clear that these are rotations. So we see that by taking this triangle, if I do nothing to it, I still have the same triangle. And this does nothing, it's an identity, it's a neutral element. If I rotate it by 0 degrees, it doesn't change my rotation. We also see that we have inverse. If I take this and I rotate it, I can always rotate it back. There's always some opposite operation. The third property, associativity, is a bit strange. And I could go through every possible combination of 3 things in every order and show that it's always the same. But I'm not going to do that because that'll take too long. There are some resources at the end of this that talk about why associativity comes up naturally when we talk about maps. In the function, it takes my triangle and maps it to a different state of the triangle. And when you have functions, they generally are associative. And we have a final property closure. If I rotate this, and then I rotate it again, it's just gonna end up being rotated. So a rotation and a rotation gives a rotation. So that means that there is some group hiding. And as I said throughout this talk, it's acting on the triangle. Now I'm gonna talk about section 3. So this part is going to be about morphisms, which describe, as I said, at the start, the sameness of structure. The idea that you can relabel things, and they still have the same structure. It doesn't matter that we call it 1, 1. I can call it bleh. And I can say blah, blah, blah becomes 3, or whatever I call that. It doesn't matter. It doesn't actually change math. Math is the same no matter what perspective you look at it. And so the first morphism I'm going to talk about is homomorphism. And this is the idea that you have one group, and you're mapping to another group. And you can't always map back. I'm going to talk about that later. But what happens is you have two elements, A and B, and you combine them to get C. But the idea is we can take this structure here, and we can actually map it to another group. And now what we end up with is we end up with x, y becomes x, y. And if we think of this map as a function, I'll call it f, and that's what's written up here. Then f of our output, c, and c is ab. So f of ab gives us our output of x, y. So f of ab gives us f of a, f of b. And that's the mathematical relation. Now, this next morphism is a bit of a stronger sense of similarity. The first one, it preserves the structure of everything. But sometimes you'll have two things that'll map onto the same thing. So for example, if you're doing modular arithmetic, right, you can map 5 to 0, and you can map 10 to 0, and all multiples of 5 become 0. It works out, your addition stays the same, but it's a smaller structure. In this next one, it turns out it's more like a similar size structure, the same size. And this is the idea that we have our homomorphism from G to S, but now we can actually go backwards. We can go back and forth as much as we want. And the way that I think of these is they're relabelings. So you can see A maps to X. I'm now calling A, the letter A, X. And if I call the letter B, Y, then saying AB becomes XY. Right? It preserves that structure. And there's this idea that it's 1 to 1 and onto, which means for finite groups, it has to have the same size. You can't have more things than one than the other, because then you'd be missing elements, and you wouldn't be able to map between them. This one also forms kind of an equivalence. So if A is equivalent to B, and B is equivalent to C, then A is equivalent to C. Which is really nice because it kind of gives us a set of all things that are the same. And we can say anything, if something's the same, then it's all the same. This next one I think is very interesting. It gives a much stronger sense of similarity again. This is the idea that we have an isomorphism, right? It maps from G to S. But an automorphism, as the name says, auto, it actually maps from G back onto itself. And you can think of this as a change in perspective. For example, if you've done linear algebra, you have vector spaces. And the idea is when you rotate, or you change your basis, it still has the same additive structure. When you add two things together, you still get the output. And this is very interesting because it says that kind of no matter which way we look at it, it's still the same, right? If we look at it this way, it's the same as looking at it this way. And this kind of gives a very strong sense of symmetry. Right? If I take this triangle, I can start here. I'm starting this way because it's kind of standard. But I could have started here, and it doesn't change the way that you think of the triangle. Michael can rotate their head. And so those are three morphisms. They're very interesting. This is kind of the main meat of the talk. The rest of the stuff is going to get a bit more complicated, and I think it's just interesting additive stuff. So now onto the long section. There's a few things I'm going to talk about here. I'm going to talk about subgroups, and then I'm going to talk about cosets and normal subgroups. So first, what's a subgroup? Well, as the name has in it, it has sub, which means it's a subset. If we have a group of things, we're going to take some things from this group and create a smaller set. The second property is this smaller set has to still be a group. So when we combine two things, we have to get there. It has to be closure. It has to have an identity. It has to have actually the same identity, because there's only one identity for a neutral element. We also have to have inverse. And associativity is actually given, because we're still using the same things. So that's what a subgroup is. It's this idea, you have a big group, and inside of it you have a smaller shell that has similar structure, contains maybe less structure. Then now I'm going to get on to cosets. Actually, cosets. So there's this idea that we have this subgroup. And what we can do is we can effectively act on it. We can multiply by something G on the left or right. And it's important to distinguish between the two because we don't have the AB is BA. We can't always switch things. And I'm going to talk about normal subgroups where you can switch things. But the idea is, if it's a left coset, you're multiplying by G on the left. If it's a right coset, you multiply by G on the right. That's the convention, it's naming. And what these give is they actually split up your group. The idea is we have our group, you have a subgroup inside, and when we map it, we get something disjoint, so it doesn't overlap. And then we get another thing that doesn't overlap, and they all have the same size. And they actually divide up our space evenly. And if you know linear algebra, you can actually think of this as you have a plane, and another plane, and another plane, and they kind of all stack up, and they all have the same size. Well, it's hard to quantify what size means in the input case.
So like GS and SG are the cosets. It's not G that's the coset.
Yeah, so the thing is you have your subgroup, and your coset is for any of your G's. You can get, G1 times S, G2 times S. Those are each cosets. So a coset is your GS for any G.
You said there's some kind of convention thing with like left and right?
Yeah,
Does
so
it-
we call this left and this right, because G is on the left and that G is on the right.
Okay.
I mean, we can call them whatever we want.
And like the left and the right G's are they different somehow from each other?
So the whole set you get is going to be different most of the time. Talking about special cases is not very useful. But it's this idea that you kind of, you could have G1S and G2S. Sorry, G1S and SG1. And those are different things, and maybe they overlap a little. Maybe they kind of split up into weird sections. I'm not going to actually be talking about this much because there are things we can do with it, but they're less useful than normal subgroups.
Wait, so what is S exactly? Is that a set or?
It's a subgroup. So it is a subset, first of all, but it also has this closure property along with it. It's a smaller little bubble in your space.
To visualize this better, you do a small example with numbers possible.
Yeah, I'm gonna get to an example. Actually, yeah, now is a good time to move on to the example. Actually, wait, this is the proof first. Never mind, I'll do the example.
It doesn't think.
So an example of this is if we have our triangle here, right? And if I just do rotation, that forms a group as I've mentioned already. But I can actually add in flipping. And when I add in flipping, this still stays a group. But you can see that rotation, you had no questions that was a group before. So this is a group, and it's contained inside this bigger group. So this is a subgroup. The idea is, I have this set of rotations. It just has 3 things in it. But I can take all of those things and I can flip them. And what I end up with is 3 rotations. And so you can kind of think of that as you have a box here with 3 things, and a box here with 3 things, and that's all your things. And it works out actually, this one, the left and right cosets are the same. If I flip it and then rotate, it's the same as rotating and flipping.
Are the different rotations the subgroups, or are the different orientations of your triangle the subgroups?
So it turns out it's actually the same thing.
Oh.
But that is a good question. The way I'm going to explain it is the rotation, the act of rotating forming a group.
Okay.
So I think, yes.
Would it be wrong to think of the act of rotating or flipping to be a mapping from one orientation to another?
That's exactly what I'm getting at.
Oh.
Yeah, that's the way I think of it. So now I'm going to do a proof. So as I said, right, if you have your cosets, wait, did I? Yeah, this should, yes.
It might be helpful to define like what the elements of your cosets actually are.
Well, are they elements or?
Yeah, no, but it's like you use it implicitly there, G1S1.
Yeah, I guess. So
What is G1S?
that's a good idea. So the idea is we have our subgroup, and we have a bunch of actions in here, right? So we have rotating, flipping, whatever. And when we multiply by G1, what we're saying is do this action and then do G1. And that creates a new action. So if we have our triangle, we have our rotation subgroup, then when we flip it, we get some rotation and then flipping, and then flipping. So it's a combination kind of thing. It's our whole composer. So here what I have is I'm going to show that each of these cosets is actually disjoint. They don't overlap. And the idea behind this is we're actually going to start by assuming they do overlap a little. Hopefully, can everybody see this area? Okay. So we're going to start by assuming that they do overlap a little. And if they overlap even just a little, that means there's going to be some element, I'll call it A, in both of them. we can actually write this as G1 times S1, where S1 is just something in our subgroup. Right? So you can think of coming from our subgroup, we go out to another set. And this is A. But because it's also on the right, we can actually do the same thing again. So we can say that this is G2 times S2. So the idea is that we have our original S, and when we multiply by G2, we go up here to A. When we multiply by G1 by something else, we also get A. And what we can do here is if we multiply both sides by the entire subgroup, by everything in our subgroup, we're actually going to get a set. And we're going to get G1 S1 times the subgroup S. And on the right side, we're going to get G2 times S2 times the subgroup S. And so this gives us, you can think of this as a different coset, but it actually works out they're the same cosets. And this is because S1 times something in S. Well, if we multiply something in S by something in S, we're going to get something in S. So it works out this actually gives us our entire group back. So we can kind of remove this S term. We're just left with S here. And we keep our G1s on both sides. And this actually shows, now this is our left coset, or one of our cosets, the coset on the left. And this is our coset on the right. And so if they overlap a little, I've just shown they actually have to be the same. Which means that if they're not the same thing, then they can't overlap. And you can kind of think of this as you have two parallel lines, right? We say they don't intersect. But really, if I have a parallel line and I put it on top of itself, then it does like intersect. It shares points. But this is saying that if it shares even 1 point, it has to share all the same points. So for simplicity, we say it doesn't intersect. Good? Okay.
So when you multiply on the right by S, are
Yes.
you multiplying by the sequence of every single object in S?
Yeah, I'm multiplying by everything in the subgroup S.
So if you multiply every single for a particular sequence of everything in S, then you'll get something else, right? But then if you multiply S1 by that, unless S1 is the identity, why would you necessarily get S back?
So yeah, this is something I did gloss over a bit, is I can show, the idea is that I'm gonna get something in S. Right? I'm not gonna get something out of S because of closures. What it works out is because S1 is invertible, it works out that S1 times big S is the same as, or is a 1-to-1 map to big S, right? Like I take something from S and I map it to something in S, and I can map back and forth. And because it's 1-to-1, if I had 3 things and 4 things, I can't line them up, I'd be missing stuff. So I have to have the same number of things. And if I have the same number of things, and they're both contained in this thing, they both fill up the entire thing. So that means that S1 S is S. Okay, I think I will move on now to Lagrange's theorem. This is the big thing in this talk. It's the probably dead person. Probably. I don't know. I haven't fact checked it yet.
Is it the same approach from physics?
I don't know.
Yes.
When did you get empire so that?
So true.
He died in
I just want-
1813.
idea for this section
Or did we?
is that we have a group G,
Yeah.
and inside of it we have our subgroup S. And what we can do is we can multiply it on the left by G1, and G2, and G3, and so on. And what's going to happen is we're going to get a bunch of cosets. And I've shown that these can't overlap, so this diagram is relatively accurate. They also have to have the same size, because it's a 1-to-1 map, right? I have to line up each thing with every other thing. And so these boxes are all the same size. And the idea is here is we can't have anything left over. If we have something left over, we can just make that a coset. We can multiply our subgroup S by that thing. So this perfectly fills up our space. And as an example, if our subgroup has 5 things in it, and we have 10 of these sets, well then we have 10 groups of 5. Not groups as in groups, 10 boxes of 5, which means we have 50 things in total. And this means that if we have 50 things in total, and 10 of these sections, each thing has to have 5. But another way you can think of this is that the number of things in S has to divide the total number of things. A good example to kind of visualize this is if we have a group with 7 things in it, and I say there's a subgroup with 3 things in it, just trust us. Well then we're going to have 3 things, and I'm going to map them, we're going to get another 3 different things. They can't overlap. And then I'm going to have 1 thing left over, and I can can multiply my subgroup by that thing to get another 3 things. But now I have 9 different things in my group of 7 things. It means I have 2 things that aren't things, which doesn't make sense. So you can't have a subgroup of 3 things in a group of 7 things. It doesn't work. You can't divide 7 by 3.
In a case where you can't divide.
No. Yeah, and that's Lagrange. It says that your size of your subgroup has to divide the size of your group. At least for finite things. It gets weird with infinite. Okay, so that's Lagrange. Now, I'm going to give some examples of things for my triangle friend.
Oh my god.
I'm going to give an example of what a normal subgroup is. So a normal subgroup, your left and right cosets are the same. Just generally what we work with, because when they're not the same, it's kind of gross. Yes.
Does normal subgroup imply a group?
No. So this is, the idea is that it gives us the same set, but the set isn't necessarily in the same order. You can think of it, like if I take this, and I have my rotations, right? That forms a subgroup. And I can take all these and flip it. If I flip them after, I get all of these states, or all of these rotations. But if I had instead flipped it first, and then rotated, I get the same things. Which means my left and right cosets are actually the same.
But isn't that what abelian is? Like the order
So
doesn't.
abelian implies normal subgroups. but normal subgroups-
It's because it has to do with the elements. So we're saying the whole set is the same, but the elements in them don't have to, right? If I rotate it this way and then flip it, I get this one, right? But if instead I had flipped it and then rotated it, I get something different. I think that's something that should be.
Is this for a particular G?
So this is actually, yeah, so this is for all G, which is why it's really nice. All G in our group. It makes sense if G is in S, then this is true, because we're just multiplying things by S, that's what I was talking about over there. But if G is not in S, that's kind of the stuff you have to check. And so that's an example of a normal subgroup I gave. And you can actually see that in these here. I have my rotations, and if I take these and I flip them, I end up with this. But if instead I had taken this and I flipped it, and then rotated it, I get the same thing. You can see these two would actually switch places. It doesn't matter, it's still the same set. An example of a non-normal subgroup is if I take this, I find first of all there's a subgroup for flipping. I just flip this way, there's 2 things, and that's it. It's closed. There's an identity. It's associative, I don't want to show that. But that's actually this set here. And if I take this flips, and then I rotate it, then I end up with these 2, which you can see up here. But if instead I had taken this, and I rotate it first, and then I flip it, you actually end up with this thing, which is different. You can see these 2 are not the same sets. So actually, our flipping here is not a normal subgroup. The cosets overlap, but they're not the exact same. So now that I've hopefully adequately defined all of these things, I think section 4 is done. We can move on to section 5. This is generally what the talk is about. This is the idea of quotient groups. It's the idea that if you have a group and you have a subgroup, specifically a normal subgroup, you can actually divide your whole group by your normal subgroup. And I'm going to kind of define this. There's going to be a lot of gross equations. I maybe should have simplified them, but I don't know. I got to scare you a bit. So these are the gross equations. No.
What?
So the product here is just a product. Because it doesn't matter what it is. It's a combination of things. I haven't defined it. Well, actually I do. I defined it right up there. So that's the definition of that product. Right? So if I have a coset G1S, and I want to combine it with G2S, there's 2 ways of thinking of this. One is I get G1, G2S. That is what I get. I just multiply the G1s. You can think I always have that S on the side. And notice I do write the S on the right. I could also write it on the left. Because it is a normal subgroup, it can kind of switch places. And if you want to check these equations, you can. I wouldn't. But this shows that there's identity, there's inverse, there's closure, and there's associated. So that means if we have this set, this box, and it contains all of our cosets, then we now know how to combine 2 cosets. We just take that leading term G and combine those, and that gives us another coset. And that means that we have some way of combining things. And that that way of combining things follows our 4 rules for what forms a group. Which means that if we take a box or a set of these cosets, they form a group. Which means that given a group and a subgroup, we can divide them, we get another group. And it works out actually, you can say things about the size of this, because we know that the number of cosets times the number of things in each of the cosets gives us our total number of things. So the size of our quotient group is actually the size of our big group G divided by the size of our subgroup. Which kind of makes sense, like it's literally division, which is also why you can't have subgroups of size 3, unfortunately, in a group of 7. And the way that I think of this is you have some group and you have some subgroup contained inside of it. This is kind of a structure. And what you're doing is you're actually taking this structure out. You can also think of it as you turn this structure into the identity. Because as you can see in this one, if we multiply by the subgroup X, it actually doesn't change anything. So you think of this, we're setting everything in this subgroup to the one element. And a good example of this is modular arithmetic. If I have all of the integers, then what I can do is I can set all the multiples of 5 to 0. I can say adding 5 does nothing. It doesn't change how many more than a multiple of 5 you have. And if I do that, well, it turns out all your multiples of 5 are a subgroup. If I have a multiple of 5 plus a multiple of 5, I get a multiple of 5. It's closed. We have inverse, every multiple of 5 is a negative. We have associativity, that's just addition. And that means that what we do is we have our integers. And when I divide by all the multiples of 5, or 5 times the integers, I'm actually left with modulo 5. Right? I'm left with 0, 1, 2, 3, 4, and 5 is equivalent to 0. So when I add 2 and 4, I get a 1. And that forms a group. So this is the idea that we can take groups, and we can take out some structure. We can stop caring about that structure. We say, multiples of 5, who cares? If it's 5 more, it doesn't change it. And that gives us another structure, another subgroup. It's very interesting. It's very useful for decomposing things. So it works out, if you can decompose into you kind of think of it as decomposing into 2 normal subgroups, and that means they kind of commute. And you can actually rewrite the original group as their product, which I haven't talked about in this talk. You can also multiply groups. It's not exactly the inverse. It gets a bit funky to think about. But yeah, I think, right, I need to give an example. This is the last thing I'm going to talk about. So, our triangle's back. We have a triangle example. So I've already mentioned multiple times, we have our group, we have rotations, and we have flippings. We have 6 total symmetries of the triangle. And our rotations form a normal sub. I gave that as an example earlier. Which means we can take our whole group and we can divide by just our rotations. You can think of this as we stop caring about the rotation of the triangle, and we look at what structure does it have. You can think we set all of these rotations to the same. We can freely rotate and it doesn't change. It's like adding 5 and it doesn't change the number. And if we do this, well, our first coset is just going to be all the rotations. And then our second one is going to be take these rotations and flip them. And we still get, well, the rotations on the other side. And so in this little caving table, which I mentioned earlier, we have a do nothing, right? If you take it and you rotate it, it's the same as doing nothing. So we've stopped caring about rotation. And if you flip it and then you flip it again, and maybe you rotate it between, it doesn't matter if you rotate it between, you're going to end up back on the starting side. Back on the side you started. And you can see if we do nothing and then flip it, it's going to end up flipped. If we flip it and then do nothing, it's also going to end up flipped. And that's a group. You can check identity, associativity, all of that stuff is here. Which this whole big talk has come up to. If we have a triangle, and I stop caring about rotations, it has 2 sides.
Let's go!
Mind blowing. But it's actually very useful, because triangles are fairly simple things. They only have 6 symmetries. 6 is kind of a small number. And we can write 6 as 2 times 3. Crazy. But there are a lot bigger groups. There are groups with millions, billions, trillions of elements. And we can talk about combining them and factoring them. There's also interesting groups, sporadic groups, because there are groups that follow patterns. Like this, we could have a triangle, we could have a square, we could have a pentagon, a hexagon, and so on. And each of those are a group. There's an infinite family of them. And we can talk about just the rotation, or we can talk about rotation and flipping. And we understand all of those. But there are groups that don't follow patterns, and they kind of show up in weird ways. And those are interesting to study. And we've actually, well, I won't get into that. But yeah, I think that is my talk. So thank you all for listening. I
feel like one of the questions that I feel like everyone
how does this connect to physics? Where is this applied to physics?
I knew somebody would ask me that question. So there's actually quite a few things. One example, I want to talk about spin. Because spin is a weird idea that I don't think is explained very conceptually. It just kind of is. But there's this idea that, let's see which time. So this idea that you have some orientation and you want to rotate it, right? And it works out, if you take a rotation and combine it with another rotation, you get a rotation. There's an inverse of a rotation. Rotation is associative, and you can rotate by nothing. It means that rotation forms a group. But when we actually want to act on the thing, we have to do something special. Because for this, I can just say rotate it, and that's pretty easy to understand how that combines. But for rotating, if we have vectors, then we want to multiply them by something. And for this, I guess I'll say it's a matrix. But what you can think of is if we have this vector and we're rotating in this plane, then we can decompose this vector into a perpendicular component and a parallel component, or a component that lies in the plane. And what happens is, it turns out that your rotation, if we call that r, if you do r times v, where v lies in the plane, it's actually going to anti-commute. This means that when you switch them, you get an inverse on your rotation. It actually rotates it backwards, if you do it in the opposite order. And this is a bit weird, because how am I defining multiplication? How can you just switch a matrix and a vector? Don't think about that too much. But it works out, they anti-commute. But it works out, if it's perpendicular, it just switches. And so we kind of want this component to stay the same, and we want this to rotate. But it works out, when we rotate it, we're kind of multiplying a plane by a vector, and we get like a volume to not a direction. So what we want to do is we actually want to multiply by r on the left and r inverse on the right. And r rotates by some angle theta. So we're doing r, v, r inverse. What happens is we decompose this, and our component that lies perpendicular to the plane, they switch. So we get r inverse v. Those cancel. We're just left with the perpendicular component. But if it lies in the plane, they anti-switch. They anti-commute. Which means we get r v, which gives us r squared. And r squared rotates by double the angle. So when we do this, this is the way we have to do this. We have our rotations, and when we act on orientations of particles, we actually get this double angle thing, where we get an r squared. Which means that if I say we have our rotation, all our directions we can rotate, then if I rotate from here to here, we get a -1 on the left, and -1 inverse, which is -1. So we get negative, and they cancel. Which actually means when I say we have something that rotates by 180, it rotates by twice that. It actually doesn't rotate it. And this is actually where half spin comes in. The idea that if I want to rotate my particle the whole way around, it works out to do that. The element in my group that does that is on the opposite side. It's -1. Which means that our group has this kind of orientation structure. And that structure has a half spin relative to the actual rotation of the particle. So that's an example in physics. I wanted to get that out there. Are there any other questions?
I didn't really understand the explanation. Is it okay if you like draw a bit on the board, just because
Yeah.
I was having a hard time following along?
So I actually might do another talk about this topic in particular,
Yeah.
and other things. I said matrices, the way that I think of it is using something called geometric algebra, cue Michael Groen. But the idea is we write some R, and don't actually, maybe, I don't know if I have time, because I only booked this room for like another 6 minutes. But I can talk about, well, I can just talk about it now, and if they kick it out.
Spin is a group.
Spin is a group. Oh yeah, also, I have to mention, this presentation template was made by Slideshow. I edited a bit, and also icons, flat icons, screen pick. I have to include this because I didn't do the paid version because I don't want to pay money.
Appreciate it.
But yeah. And these are a bunch of resources that I recommend. The first one is really long, but it's effectively a comprehensive cover of everything I've talked about and more. It's like 2 hours. This explains why associativity shows up when you're talking about composition of functions. As you mentioned, this rotation and symmetries of a triangle are functions. They take a triangle to its function. And this is an introduction to group theory. And it's funny because I only watched halfway through this video, and I watched it like after making my presentation, and it works out that the example they use is a triangle. And the reason why is it's actually the first group with non-normal subgroups. So anything smaller has normal subgroups. And then it feels a bit silly to talk about normal subgroups and everything's a normal subgroup. No, Michael. talking about spins or however much want to take this in here. So we have vectors, right? I can say I'm going to define I hat, j hat, and k hat. It's my x, y, and z direction. And for geometric algebra, we define a vector squared, like multiplied by itself. And we call this the geometric product, is equal to the magnitude of that vector squared. Kind of makes sense. It's a dot product, kind of measures itself and gives you its length squared. But from this, if we actually look at, we also say that the geometric product distributes, which gets into rings, but I'm not going to talk about that. So what we have is we can write v as some x I hat plus y j hat, and then we can multiply by itself. And if we actually distribute this, we use FOIL, we're going to get x squared I hat squared. And also, scalars commute with vectors, something that I have to mention. Vectors do not always commute with other vectors. They sometimes do, like I commutes with I. If you switch I and I, you still get I times I. So we get this plus y squared j hat squared plus xy ij plus yx ji. And we know that this has to be the length of a vector squared. And we know what the length of something going x here and y here. We use Pythagorean theorem, we get x squared plus y squared. This is equal to x squared plus y squared. Which means we can actually, because I hat squared is 1, and j hat squared is 1, they're unit vectors. They square to the magnitude squared, and magnitude squared is 1. This is actually something you do have to define. You have to define what your unit vector's length squared is, because you can actually say it's -1 or 0, and you get completely different spaces, and rotation works completely differently. And I might be talking about this because actually, if you have a time direction vector and you define its magnitude to square to -1, you actually get space-time rotations, and you get things like a light direction has 0 length, which means as you rotate, it never changes, which is really cool stuff. But we have x squared plus y squared here and x squared plus y squared here, so we can cancel them both. And now we have xy and xy, so we can actually divide by xy, assuming we're going to say one of them isn't 0. Sorry, both of them aren't 0. We can pick any vector. What we're left with is I hat, j hat is equal to, plus j hat, I hat is 0. And this actually means that I hat and j hat actually anti-commute. What's really cool is this allows us to kind of filter out our bivector component and our scalar component. Because as you saw here, what we get is we get a scalar. And this thing with these two vectors is called a bivector. So this is actually what it is. It doesn't simplify any further. It's like writing 1 plus I, a complex number I. You can't reduce that, it just is. And so what we can actually write is if we have a vector v and a vector u, and you multiply them. I'm just not going to put all the hats because it's annoying. Everything here is a vector. And add them with u, v. And this means that our bivector part will actually become negative because we've switched them. And it actually cancels out. So we're only left with the scalar part. Well, we're left with 2 of them. So we divide by 2. It works out our scalar part is the x component times the x component plus the y component times the y component. Also, all of this generalizes to 3D and 4D and beyond. And so what this actually is this is the dot product. And the dot product commutes. This is the commuting part. Yes.
So this is just some operation that you've defined. It's not an inner product or another product or anything.
Yeah, I can actually show you what it is in terms of those in a second. So we have that. And then what we do is we say, well, what if we have a negative there? Like vu minus uv all of the two. Well, this, the commuting, the scalar part that commutes, is going to cancel. So we're going to get it in both terms. We're going to subtract it. But the anti-commuting part is going to be here. And then we're going to have a double negative. So our bivector part actually stays. And I mean, this is what is called the outer product of u and v. And so this means, if we actually add these together, we get vu. These terms cancel out. So we can actually write v, sorry, I gotta stand in the way for a second. vu is equal to v dot u. So this is v outer product u. It does matter. It's equal to vu plus v outer product u. You add the inner and outer product and you get the total product. Makes sense. Crazy. So this is the whole thing. An interesting property we have is that I hat j hat squares to -1. multiply things, I can raise them to powers. And what this actually gives me is, because this squares to -1, it gives me the same thing as Euler's identity, if I had used the complex number I. So this gives cosine of theta plus I hat j hat sine of theta. And when I multiply this on the left by a vector, I'm going to get cosine times that vector, which is going to cut it in parts. And then I'm going to get a sine component rotated 90 degrees. Because when I multiply I hat j hat by j hat, it becomes I hat. We rotate 90 degrees the other way. And if I rotate I hat j hat by I hat, it's a negative sign. So this rotates by 90 degrees. It gives me a sine component in that direction. Which means what I've done is I've taken my vector and I've rotated it by theta degrees. So this is our rotation thing that I was vaguely alluding to. Yes.
It looks suspiciously like quaternions.
Yeah, so it actually turns out that quaternions are actually contained in this structure. It works that if you take only your I hat j hats, then you have a plane here, and a plane here, and a plane here. And those three actually give you your unit quaternion vectors, numbers, and one is just one. And it also works in the two-dimensional case, but this is the complex number. So you get complex numbers, you get quaternions. You also just get general vectors. You get rotation, and you can do rotation in space-time. It's very general. I think it's a good tool for understanding, but it's harder to do calculations though. That's the thing. When you're working with all this stuff, it gets very messy. Because you have to keep track of everything, and what commutes and what doesn't commute, and you have to separate things and put them back together. And it's generally a pain. But yeah, so we have this thing, and it rotates. And what happens is, if we have I hat, j hat, times a perpendicular component k hat, what works out, I have my two things here, and I have my k hat, like this. And I can switch it once, which gives me a negative sign, and I can switch it again, which gives me two negative signs. So this is actually equal to k hat, I hat, j hat, and also k hat commutes with my scalar here. Which means that this thing, I'll call it r sub theta. Well, r sub theta times k hat is equal to r theta, sorry, is equal to k hat r theta. It commutes. And this also works if theta is negative, which gives r inverse. It rotates the opposite way.
It looks like a parity theorem kind of thing.
Yeah, it is. It forms a symmetric alternating group.
Well,
Same.
alternating instead of even so.
Yeah, it would be.
So this might be a naive question, but so is like the conservation laws or like time translation symmetry or like rotational symmetry, like is group theory like lying behind that?
Yeah.
Okay.
Yeah, it's the idea that it's a symmetry of the universe. If you think of a point space, I guess, it's not quite a group. The idea is, yeah, when you change your reference frames, you can think of it as translation, and translation forms a group. It actually works out translation.
Oh my God, yes.
Yeah, you describe
Yes.
translation as vectors. So vector
Okay.
spaces are the symmetries of a set of points. Okay, and more, as Michael would like me to mention. They're not just that.
Okay. Yeah, because okay, in quantum we learned right the rotation matrices, they form a group.
Yep.
Right.
Yeah, so actually, it works out, if you've heard of polyspin matrices, these things are actually your polyspin matrices. So you can actually write these as matrices, which is what most people would do. But I don't want to write out a big matrix. Also quaternions, it's a bunch of structures. But yeah, so you have a question? Okay. So yeah, we have this property that it switches. But if I have I hat, j hat, I hat, well, when I do one switch, it gives me a negative. But then I hat and I hat switch, they're literally the same thing. You can't tell the difference between the two.
I guess I had a comment about like symmetry, is that
Yes.
group theory inherently talks about symmetries
Yes.
in various different ways. So talking about applications to physics, essentially any situation in which you will see some sort of symmetry, whether it's like conservation laws or whatever, usually group theory is underlying it all.
Yeah, another example of like symmetries that you might not think about is path independence. Because paths actually form a group. Because if they have a direction, you have to include direction in the function. If you have a path going this way, there's an inverse. You can add a path going backwards, and they cancel. And if you have nothing, then it doesn't do anything when you add it. But then it gets a bit funky because you want your paths to be continuous. So like, when I say that, there's a whole lot of things that you have to talk about and assume and work out. It is highly abusive. Yes.
But okay, so here's my naive question. You know how you were saying, oh, we can just forget about the rotation of the triangle?
Yes.
So when we have like rotation symmetry, that's like a subgroup? Like
Yeah.
you took that,
Yeah, well,
or
the idea
is it not?
Every group can be thought of as a subgroup. A subgroup is right? You just have to make a bigger thing of a group. And
Okay.
actually, it turns out a group is technically, by definition, a subgroup of itself. Because it's a set of elements from the group, and it's also a group. So every group is a subgroup.
But it's a subgroup of a specific, isn't it like every group is a subgroup of a free group?
Yeah, that's something else too. The idea is you can just not put restrictions on what your operation does. So I can just say you have a bunch of symbols and you can combine them. And I'm not going to tell you what they simplify to. I'm not going to tell you what AB is. And it works like that actually gives you the whole group structure. But the idea is you actually, when you reduce this, when you say that AB is BA or AB is C, it gives you a smaller group containing inside. We generally, free groups are interesting because they do actually contain every finite group. And some infinite groups. And it's really hard to talk about the structure. If you could describe the structure of a free group, then you would know the structure of every group. The problem is the free group has no rules imposed on it. So you can't really talk about the structure. I mean, you can say things like it's associative. You know, if A times B is A, then B has to be the identity. That's true for all groups. I can say those things. Yes.
Would that mean that the free group is a group of groups?
It's not a group of groups because it's still a group of things, right, or elements. You can talk about groups of groups. It gets very complicated. There's some things like something called an automorphism group, because I talked about automorphism. It's that change in perspective. It turns out there's always an inverse because it's a one-to-one map, and you can always compose two automorphisms. And there's a map that maps every element to itself. That's the identity. So it works out if you have a group, you can actually create a group of automorphisms. And you can actually create a group of those automorphisms, and so on. Yes?
So what is the group of all groups that doesn't contain itself?
I don't want to get into that. It gets interesting though. And there's interesting things like, there's some things you can talk about free groups. Like the idea that every free group is isomorphic to writing symbols on a piece of paper, right? And that's a group action. I'm acting on the paper. I can write a symbol. I can write another symbol. I can erase that symbol. I can erase a different symbol. There's inverse. There's composition. If I write A and then I write B, and then I write C, it's associative. It doesn't matter what order I write them. It only matters their position. It works out. Writing symbols on a piece of paper forms a free group. It means that every group can be represented or is contained in the act of writing symbols on a piece of paper. Which is how we can do math. If that wasn't true, that means there would be groups that we couldn't describe on paper. And it would be really hard to talk about. And there are some weird groups that are infinite and really hard to describe. There are things you can say.
May I add a comment about how group theory is used in physics?
Sure.
So you have, for instance, paths, and you can find their length by integrating over a parameter. And you find that you can change your parameter and still get the same length. So you have reparameterization invariance. And that is a symmetry of a diffeomorphism group. So now what you do in loop quantum gravity is that you go the other way around. You start with diffeomorphism groups that kind of look like quantum-y stuff. And you say that these generate some conserved quantities, like area operators or volume operators and things like that. So you can quantize length and things which are usually like conserved classically and turn them quantum.
I also feel like I should comment, one of the most common groups that you would meet in class is matrix multiplication, as compositions of matrices forms a group. So, or it's called a general linear group. We can talk about special linear group, which are all determinants 1 or whatnot that somewhat preserves lengths or whatnot. And one of the biggest, I feel like, application of groups is Lie groups. So it's a group that has a manifold underneath, and then you can talk about a million other structures of it and its algebras, and then things get very complicated really fast.
It's good stuff. There's a lot more to talk about in finite groups, infinite groups, integers, all of these things. It's a very deep subject. I mean, it's a whole field study, and this is just an introduction.
Pun intended.
No, I'm not. Yeah. Should I finish up this example? We've got a bit off topic. Yes, no?
Finish that.
Okay, I'll continue this. So, as I was talking about, if you have an element in the plane, right, it actually anti-commutes. And so if we switch this I and j here, then we're going to get a negative sign. But then when switching I with I, it doesn't do anything. So this is actually negative I, j, and I'll put brackets around these to show that this is negative switching. And we're saying negative ij is actually ji. It rotates in the opposite direction. So in general, what we have is, if we have, you can also think, if we put a negative here, we can suck it into the sine theta. We get sine of negative theta. And it also is cosine of negative theta. Cosine of negative theta is the same as cosine of theta. So it switches our angle. It means if we write our vector as a component in the plane perpendicular, if we look at r theta b, r minus theta, then what happens is, if it's perpendicular, it commutes. So we're just going to get b perfect. And then if it's parallel, it anti-commutes. So this theta becomes negative. It's a double negative. So we get r theta, just r of 2 theta times our b. And you can think of, if we just took one of these r's, they form a group, right? And this is actually, this is the idea of group action. This is some of the more things you can do with it. Because we have a vector space, and that's a group. But then we have a group acting on a group. And sometimes we'll even talk about a group acting on itself. So you can talk about what are the symmetries of your structure? What are the maps from your structure onto itself? And what do those kind of compose together? But yeah, and so this 2 theta here means if we rotate our particle by some theta, we have to multiply it by our element in our group that we rotated by half the end. Hopefully that clears things up. What else should I talk about?
I have a question.
You have a question?
So when I was taking particle physics, we also talked about representation theory. Is that like within group theory, or is that like a whole different thing? Because I didn't understand what it was.
Yeah, I mean, I think it's related to group theory, definitely. It's the idea, I think, of isomorphism, right? It's that idea of similarity.
Yeah.
You can think of, for example, when I was talking about free groups, the idea of writing it on a piece of paper, that is a representation. I think. I haven't done any courses in this formally. But the idea is that we have some structure, and we want to find a structure we can actually work with, that we can actually see and use and visualize. And to do that, we want to find a one-to-one map. Because then it's just a relabeling. It's a representation. I'm assuming there's more to representation theory. I haven't learned too much about it.
It was like irreducible representations present like, I think each irreducible one was like an important, I forgot.
That may be related to rings.
I don't know.
I'm not sure.
Okay, thank you.
Representations.
Representation.
Why vector I call that representation?
Wait, were you at the Ash Row event?
No.
Somebody else made that joke. Holy Mike, yeah. Like, 5 vectors don't exist.
Oh,
Sad.
well, man.
Sad. No Bible representation.
Tragic.
Okay. I think I might talk about silo P subgroups,
Oh, no.
which are, it's
Alright.
gonna be.
Let's get to it.
Did you know that
Rip the Band-Aid off.
Did you know that it's actually not SIBO?
SIBO?
It's SIBO, I think, with
I was
like,
about to say SIBO.
yeah.
I
David
didn't-
McKinnon was talking about that, cause like,
Yeah.
SIBO was like English and
Yeah.
I,
Yeah.
not in fact,
Yes, I
I go back to
And like, the ground Ruby Lagrange things are
How would it work? Like, cause
he had like,
paper,
he did the thing where you like,
like,
immigrate at a young age.
kind of
I think.
expanded, I guess, with certain things. You have three things, you have like independence, objectivity,
I can also probably turn this off.
and the deterministic, yeah, like, it's like your system can't only be two